Right, in this video, we're going to talk about section 4.5 dealing with optimization problems. And out of this video, we're going to solve optimization problems that involve geometry, number operations, and conic sections. Also, we'll optimize the sum, product, or squares of two numbers given constraints, and also we'll solve applications by optimizing functions. All right, so this section does deal with optimization, which is a topic that arises in many disciplines that rely on mathematics. And here's some examples. A structural engineer might seek the dimensions of a beam that maximizes strength for a specified cost. Or a packaging designer may seek the dimensions of a container that maximize the capacity of the container for a given surface area. Airline strategists need to find the best allocation of airliners among several hubs in order to minimize fuel costs and maximize passenger miles. Okay, so in these examples I just mentioned, what we're trying to do here is find an efficient way to carry out a task. And the word efficient could mean the least expensive, the most profitable, the least time consuming, or as you'll see, many other measures. Okay, so this deals with the material that we talked about back in section 4.1 when we were dealing with maxima and minima, and also finding, of course, increasing and decreasing, which will help us determine local maximum and local minimum. We're applying all of that to these problems that deal with optimization. Okay, and here's some guidelines for optimization problems. Number one, you want to read the problem carefully, and that is identify some variables and organize the given information with a picture. Sometimes pictures does help in solving these type of optimization problems. Second, identify the objective function. That's going to be the function we're trying to optimize. I'm going to write it in terms of the variable of that problem. Then number three, you're going to identify the constraint. And in this case, you're going to write them in terms of the variable of the problem. And then use that constraint to eliminate all but one independent variable of the objective function. So with your constraint, you might have to, write it in terms of just one variable and then substitute it in the objective function. So that way your objective function will be in a single variable. And with that objective function expressed in terms of a single variable, you're going to find the interval of interest for that variable. And then finally, you use methods of calculus to find the absolute maximum or minimum value of the objective function on the interval of interest. And you might have to check the endpoints if necessary. Okay. So now let's look at, and in this video, I have like 5 examples. Let's look at this first example here. What two positive real numbers whose product is 13 have the smallest possible sum? And in this case here, we're going to let S be the sum of the two numbers. We want the objective function in terms of one number, which is X, then the interval of interest of the function, and then find out what those numbers are with the product of 13 and give us the smallest possible sum. All right, so I'm going to do this on a separate sheet. All right, so in this example, number one, here we're going to be looking for two numbers here, two positive numbers. So that means I'm going to let's say X equal to the first number And for the second number, I'm gonna let y be that. All right, so we're looking for two positive real numbers whose product is 13. So that means that the product of x and y, or x times y, must equal to 13. And the other would be where you're going to have the smallest possible sum. So that means I'm letting capital S be the sum of those two numbers, x and y. Okay. So I need to come up with an objective function for this. So let's do this. I want this S, because in the problem, they want S is equal to what? So that means S has to be in a single variable. That means I'm gonna let S be in terms of X. That would mean I need to find out what Y is in this equation. X times Y is equal to 13. So if I solve for Y, I'll need to divide both sides by X in this equation. So that means Y is equal to 13 over X. And then next, I'm going to substitute this Y in the S formula with 13 over X. So this would be S is equal to X plus the Y is equal to 13 over X. Now this represents the objective function in terms of X. So in this case right here, my S will be equal to X plus 13 over X. Okay. And now let's find the interval of interest of this function. Now, in this case here, we're looking for two positive real numbers. That means X cannot be negative. And also X can't be zero because I would get a zero in the denominator for this objective function. So the interval that I will be dealing with is going to be from 0 to positive infinity. And those I put parentheses for the 0 because I cannot include 0 because I would get a 0 in the denominator. So that would be the interval of interest for this function. Now we're going to be using the concept of finding the first derivative and then setting it equal to 0 to find out what our critical points are going to be, or critical values in this case. So my objective function is S is equal to X plus 13 over X. And in this case here, what I'm going to do here is write 13 over X as 13 times X to the negative 1 power. So here's what I'm going to have. S is equal to X plus 13 times X to the negative 1, because that X is like X to the 1. So if I pull it out of the denominator, it'll become negative for that exponent. Then I'm going to take the derivative of this. Well, this is in terms of X, so I'll say X, S prime of X. The derivative of X will be 1. Now for 13X to the negative 1, if I bring the negative down, multiply by 13, I'll get minus 13, X to the 1 less power. 1 minus 1 would be negative 2. Then I'm going to write 13X to the negative 2 as a positive exponent. So this will be 1 minus 13 over X squared. So this is what S prime of X will be. And then I'm going to take that s prime of x and set that equal to 0. So I'll do this over here, s prime of x, that will be equal to 0. And s prime of x is that 1 minus 13 over x squared. That's equal to 0. And then next what I'm going to do here is multiply both sides of this equation by that x squared since it's in the denominator. So I'm going to multiply both sides by 13. And if I distribute the 13 on the left side, 13 times 1 will be 13 minus 13 times 13 over x squared. I'm sorry. I'm trying to get rid of the x squared in the denominator, so I need to multiply both sides by x squared. As y'all can see, I'm having one of those senior moments here. Now, x squared times 1 will be x squared minus x squared times 13 over x squared. The x squareds divide out, you'll be left with 13 is equal to 0 times x squared will be 0. So I have x squared minus 13 will be equal to 0. And then if I add 13 to both sides, I get x squared is equal to 13. And now to solve for x, I'm squaring it, so I take the square root on both sides, and I do include that plus or minus symbol when you take the square root on both sides. So that means I'm going to have x is equal to plus or minus the square root of 13. Now what that means here is this, that x is equal to the square root of 13, and x is equal to negative square root of 13. But the restriction here is from 0 to infinity. And negative square root of 13 is outside that interval of interest. So that means I need to cross that out. Because that negative square root of 13 is outside the interval of interest. But the square root of 13 is inside the interval of interest from 0 to infinity, which is this. All right, so x will be equal to the square root of 13. Now let's find out what y will be equal to. Now we let y equal to, if you recall, I'm gonna bring this back down, 13 over x. So I'm going to substitute the x with the square root of 13. So that means I will have 13 over the square root of 13. Now they want you to rationalize the denominator. I'm going to tell you that in the homework they want this answer to be in simplest form, meaning we need to rationalize the denominator by multiplying the numerator and the denominator by the square root of 13, because they want that radical out of the denominator. So the numerator will just be 13 times the square root of 13 divided by the square root of 13 times itself will give us what's underneath that radical, which is 13. And if I divide out the 13s, you'll be left with the square root of 13. Okay. So going back to this, okay, the interval of interest for the function is, of course, from 0 to infinity. Let me fill that in. And the numbers that we were looking for that gave us a product of 13 with the smallest possible sum are the square root of 13, and the other one, square root of 13 as well. So all of that was example number 1. All right. Now, example 2 on your handout looks like this. A rectangular pen is built with one side against a barn. If 2,000 meters of fencing are used for the other 3 sides of the pen, what dimensions maximize the area of the pen? Okay. And then in part B, a rancher plans to make 4 identical adjacent rectangular pens against a barn, each with an area of 25 square meters, as indicated in this figure, as you can see. What are the dimensions of each pen that minimize the amount of fence that must be used? Okay, let's tackle part A first, and then we'll go into part B. All right, so we're dealing with a rectangular pen, and that's going to be built with one side against a barn. All right, so I'm going to draw a figure here. So this is example 2, part A. All right, let's say we had this. There's a barn right here. All right, and we just got 2,000 meters of fencing. That's going to be used for the other 3 sides of the pen. Okay. All right, in this case here, we got 2,000 meters of a fence that's going to be used for the other 3 sides of the barn. And it's going to be in the form of a rectangle, since we're dealing with a rectangular pen. Now, of course, there's one thing you need to know. For the area of a rectangle, that's going to be equal to length times width. There are geometric formulas that you do need to know regarding area and also volume and surface area as well. So you might as well be aware of that. Okay, now we're going to do 2,000 meters of fencing here. This part right here represents 2,000 meters of fencing, and it's going to be in the form of a rectangle. And in a rectangle, you should know that the opposite sides of a rectangle will have equal length. So if this side right here is going to be represented by X, then this side opposite that will be represented by X. Now, for the length of this side, if I add X plus X, that's 2X. This remaining side will have to be 2,000 minus the 2X. That 2,000 represents the amount of fencing that we allotted. And then we're going to subtract out the lengths of these 2 sides here that are opposite of each other. X and X is 2X. So 2,000 minus 2X represents the remaining length of that side. Okay. Now the area of the rectangle, of course, is length times the width. That would mean A is equal to, the length here is 2,000 minus 2X. Times the width of one side, that's this width right here, would be X. So now I have an area formula for this right here. So if I distribute the X here, this will be A is equal to 2,000 times X will be 2,000 X minus 2X times X will be 2X squared. That represents this area right here of the barn, of the rectangular pen. 2,000 X minus 2X. Okay. Now in the homework, they're telling you to let A be the area of the rectangular pin and B and X be the length of the sides perpendicular to the barn. The objective function in a form that does not include the length of the side parallel to the barn is going to be what I just came up with, 2000x minus 2x squared. Now they also ask for the interval of interest of the objective function. Well, let's take a look at this. We know that our lengths can't be negative. So we can leave out any negative values for x. But what I'm going to do here is take that 2000x minus 2x squared and set that equal to 0, okay? Because at some point, my x values will be too big where this length right here will end up being negative, okay? I got a better idea. Instead of setting 2000x minus 2x squared to 0, let's just set this length right here of 2000 minus 2x. Set that equal to 0 and find out maximum length this could be. Okay. So if I move that minus 2x over to where the 0 is, this will be 2000 is equal to 2x. Then divide both sides by 2. X will be equal to 1000. So x can be no more than 1000. And that's because if it's more than 1000, then this length with 2000 minus 2x, that would be negative, and we can't have a negative length. So the interval of interest will have to be, and this will be the closed interval from 0 up to 1000. Okay. Because it's okay for these two lengths to be 0 here. That would mean the whole thing, the whole fence will have to be 2000 meters. Or the length of that side will have to be 2000. So the interval of interest would be from 0 to 1000. And now from here, we can answer this part right here, finding the dimensions that maximize the area of the pin. All right, so let's take our A, this formula right here, and I'm going to write this as A of X, since it's in terms of X, equaling to 2000 minus 2000X minus 2X squared. 2000X minus 2X squared. And then take its derivative. So A prime of X would be, the derivative of 2000X would be 2000 minus the derivative of 2X squared would be 4X. And then from here, we set A prime of X to be equal to 0. Which will be 2000 minus 4x equal to 0. And then we just solve for x. So if I move that 4x over to the other side, this will be 2000 equals to 4x. Divide both sides by 4. X will be equal to 500. And this is in meters, by the way. So that means the x, which is going to be, and I'll bring this back down, the length of this side, both this side on the left and on the right, will be 500 meters. So now to find this length here, And by the way, that 500 equal to X, we call that the local maximum. Since we're maximizing, this will have to be your local maximum. Okay. So now for 2000 minus X, I'll do this over here. 2000 minus 2X, I should say. We just substitute the X with 500. So now you got 2 times 500, which is 1,000. 2,000 minus 1,000 would be 1,000. And that would be in meters here. Okay. So to answer that question, to maximize the area of the pen, the sides perpendicular to the barn, that's this side and this side, should be 500 meters long. And the side parallel to the barn is the side parallel to this barn, must be or should be 1,000 meters long. Okay. So that's how we answer part A of example 2. All right, on the next page, I'm going to do part B. Bring back up part B. And that's this. In part B, it does say here, A ranger plans to make 4 identical and adjacent rectangular pens against a barn, each with an area of 25 square meters, as indicated in this figure. What are the dimensions of each pen that minimize the amount of fence that must be used? Okay, so I'm going to draw another figure here. Okay, so here's our barn. But this time we're going to have 4 identical and adjacent rectangular pens against the barn. Each will have an area of 25 square meters. So here's that. I'm going to have 4 equal pens. And keep in mind, these, when I'm drawing, it's not drawn to scale. So each of these has an area of 25 square meters. Okay. Now, the formula for finding the area of any rectangle is going to be this. Area is equal to, and I just say A is equal to length times width. Now, here if I let X be this length right here, now keep in mind here, I'm going to have fencing here. So if this length is X, the length of this fence right here will also be X. The length of this fencing will be X. The length here is also X. And this length here on the end will also be X. So I have 5 lengths each of length X. 5 lengths of fencing, each with a length of X meters. So that means here that this width right here, since area is equal to length times width, and I know that each one of these is going to be 25 square meters, so this will be 25, is equal to the length, which is of course X, times the width. I'm going to let that be W. And here I'm going to solve for W by dividing both sides by X. So that means your width would be 25 over X. That means each one of these lengths here that I have marked off would be 25 over X. This length here, 25 over X. This length here, also 25 over X. And the same thing here, 25 over X. That would mean if I take the total length of the side parallel to the barn, the total length of the side parallel to the barn, that's this right here. There are 4 of them, so it'll be 4 times 25 over X. And that 4 is like 4 over 1, so 4 over 1 times 25 over X will be 100 over X. So this whole length here is 100 divided by X. So this is what's going to help me find out what the L is for part B. We'll let X be the length of the sides perpendicular to the barn. So here, that's what that is. That's what we're doing here. And L is going to be the total length of fence needed. So the objective function is going to be this. And I'm going to call this L of X. And that's equal to, all right, these are fencing right here, each of a length of X. So there are 5 of them. So it'll be 5X plus the total length of the side parallel to the barn. That's 100 over X. All right, and this right here is going to be your objective function. L equals to 5X plus 100 divided by X. That's the objective function. All right, next is the interval of interest that they want. Well, we should know that lengths can't be a negative value. And of course, if you look at this, we can't have a 0 in the denominator. So in this case, my interval of interest for this would be from 0 to infinity. Okay. So it's just going to be all positive numbers here. So the interval of interest of the objective function will be from 0 to infinity. Okay. So now we're going to answer the question of this. We want to find out what are the dimensions of each pin that minimizes the amount of fence that must be used. So here we're minimizing the amount of fencing that must be used. All right, in this case here, let's rewrite this using negative exponents and then take the derivative. So here we're going to have L of X is equal to, and in this case, 5X plus 100, that X comes out of the denominator as X to the -1. And then take the derivative of that. So L prime of X would be, the derivative of 5X will be 5. Now, if I bring the -1 in front, it'll be minus 100. Copy the X down to the 1 less power, -2. And then I'll go ahead and rewrite that using positive exponents. So it'll be 5 minus 100 over X squared. And then we're going to set that derivative L prime of X to be equal to 0. So L prime of X was 5 minus 100 over X squared. And that's going to be set equal to 0. Now, since I got that X squared in the denominator, I need to multiply both sides by X squared in this equation. Left side, multiply that by X squared. The right side, multiply that by X squared. So X squared times that 5 will be 5X squared minus 100 over X squared times X squared. The X squares divide out. You'll be left with 100 equal to 0. And then next we're going to get X by itself. We need to first add 100 to both sides. So that means I'm going to have 5X squared equals 100. Divide both sides by 5. X squared would be equal to 20. And then if I take the square root on both sides, I'm going to leave off the plus or minus and just deal with the positive part because we know length can't be negative. Okay. So the square root of X squared would just be X, and that's equal to, for the square root of 20, I need the largest perfect square that goes into 20. Because in the homework, they're going to want you to type in your exact answers using radicals if needed. So the largest perfect square that goes into 20 will have to be 4. That'll be multiplied by 5. And the square root of 4 will be 2. So the X is equal to 2 square roots of 5. Okay. So each of the sides perpendicular to the barn, that's this side right here, each of these should be 2 square roots of 5 meters long. Now they ask for each of the sides parallel to the barn. That means, if I go back down here, up here, this side, this side, this side, and this side, they want the length of each one of those. All right, so if you recall, the length of each of these sides is 25 over X. All right, so let me write here the length of each side. Was 25 over X. And we found X to be 2 square roots of 5, so it'll be 25 over 2 square roots of 5. Now, since I got that radical in the denominator, let's multiply the numerator and the denominator by the square root of 5, so that way I can get that radical out of that denominator. So bring over the 25 square roots of 5 over 2 times the square root of 5 times itself will be 5. Okay, the idea there is to get rid of that, to wipe out that radical by multiplying the square root of that number times itself. When that happens, your radical is gone. All right, so now let's simplify this a bit. Well, I know 5, this 5 goes into this 25 5 times. So I'm going to end up with 5 square roots of 5 over 2. That represents the length. I need to bring this back down here. The length of each of these sides here. That's 5 square roots of 5 over 2. So going back to this, the length, each of the sides parallel to the barn should be 5 square root of 5 all over 2 meters long. Okay. All right, Now, example 3. So here's example 3. We're going to find positive numbers x and y satisfying the equation x times y is equal to 30, such that the sum of 5x plus y is as small as possible. So in this case, let's say we got this. Okay. We're looking for positive numbers satisfying the equation x times y is equal to 30. So that's one equation, such that the sum, and that's going to be capital letter S, equaling to 5x plus y, is as small as possible. Well, let's get this equation right here, your S, in terms of x. So in other words, for this equation, x times y equals 30, I need to solve it for y. And I'll do that by dividing both sides by x. So that means y is equal to 30 divided by x. Then I'll take that 30 over x and substitute it for y in the equation for s. So the s is equal to 5x plus y, which is 30 over x. So this represents the objective equation. Okay. So let's say the objective equation is at 5x plus 30 over x. That's your objective equation. All right, and let's say I want to find the interval of interest. The interval of interest. Well, if you look at this, we're dealing with positive numbers x and y. Positive numbers x and y. So we know we can't have negative numbers. And also, we're not going to be able to use 0 because I'm going to have a 0 in the denominator for this objective function. So that means the interval of interest would be from 0 to infinity. So if I go back to this, the interval of interest would be from 0 to infinity. And now we can go ahead and find those positive numbers x and y, where x times y is equal to 30, and the sum, 5x plus y, is as small as possible. So we'll take our objective function number, write this as s of x, since it's in terms of x. That's equal to 5x plus 30 over x, and take its derivative. Well, before we do that, let me write this as 5x plus 30 times x to the negative 1, and take the derivative of that. So now s prime of x will be, the derivative of 5x will be 5. Now, if I bring down the minus 1 or the negative 1, it'll be minus 30. Copy over the x to the 1 less power. So it'll be 5 minus 30 x to the negative 2. And using positive exponents, it'd be 5 minus 30 over x squared. And then next I'm going to set s prime of x equal to 0 and solve for x. So I'm going to have 5 minus 30 over x squared, and that's equal to 0. And then next I'm going to multiply both sides by the x squared so I can get rid of that x squared in the denominator. So this will be multiplied by x squared. The right side will be multiplied by x squared. So x times the 5 will be, x squared times the 5 would be 5x squared minus 30 is equal to 0. And then next I'm going to solve for x by adding 30 to both sides. That would mean 5x squared would be equal to 30. Divide both sides by 5, you'll get x squared is equal to 6. And here I'm just going to take the positive square root because I know length can't be negative. So take the square root on both sides. It'll be x is equal to the square root of 6. So one of the numbers there will be x is equal to the square root of 6. Now for the y, if you recall, y was 30 over x. So let's use that to find the other number. So it'll be 30 divided by the square root of 6. And of course, we rationalize the denominator by multiplying the numerator and the denominator by the square root of 6. So I have 30 square root of 6 over the square root of 6 times itself will be 6. 30 divided by 6 will be 5, so it'll be 5 square root of 6. Okay. So to answer the question here, the numbers that we're dealing with are the square root of 6 and 5 times the square root of 6. I'll make my 6 look like a 6. All right, those are the positive numbers where x times y does give me 30, and the sum of 5x plus y is as small as possible. Okay. And while I'm at it, feel free to pause the video if I'm going too fast for you with these problems and you need to write this down, just feel free to pause. All right, now example 4. Here we got a rectangular tank with a square base, an open top, and a volume of 19,652 cubic feet. And that is to be constructed on sheet steel. Find the dimensions of the tank that has the minimum surface area. Okay. All right, there are some things that we need to know. We know we got an open top, and we also have a volume given to us. And we also know we have a rectangular tank that has a square base. Okay, so what I would do, I would draw an open tank, a rectangular tank in this case. Okay. And by the way, this is example 4. I'm going to draw a rectangular tank. The base is going to be in the form of a square, by the way. And again, this is not drawn to scale, so bear with me on this. And you really gonna have to bear with me on this here. In this case here, let me do a dotted line coming this way. And then another dotted line going this way. And y'all have to bear with me because my drawings are not that great. I'm not a good of an artist these days. Might be good at math, but not in art. All right, there we go. So that is a rectangular tank, and it does have a square base. All right, now, there's a couple of formulas that we do need to be familiar with. One is going to be the surface area of a rectangular, and I'm going to abbreviate rectangular prism. I'm going to use SA for surface area. Usually the formula for finding the surface area of a rectangular prism would be this: 2 times the length times the width, plus 2 times the width times the height, plus 2 times the length times the height. And what I mean by that is this: the length times the width would be these 2 bases, the one on the bottom and the one on the top. The width times the height would be the lengths on the sides, the one on the left and the other one on the right, and then 2 times the length times the height. That's the front and the back of that prism or box. Okay. So that's what we mean by a rectangular prism or rectangular box here. All right, now in the problem, they do say, let S be the length of one of the sides of the square base and let A be the surface area of the tank. And here I want to write the objective function. All right, so let's start by labeling this side S, and this side is also going to be S. This will be H, that would be your height. And I also need to mention something else. It does say an open top. That means we're not going to include the area of the top, okay? Which is, of course, length times width. So we're only going to be dealing with one of the lengths times the width, which is just the one on the bottom. So this surface area for this rectangular tank is just going to be length times the width, because we're not including the one on the top because it has to be an open tank. We're only concerned with the one on the bottom. The sides, the lengths of the area of the left and the right is going to be 2 times the width times the height. And the area of the front and the back would be 2 times the length times the height. Okay, that's going to be our formula here that we will use here. Okay, keep in mind we're not including the one on the top, so that's why it's length times width. This represents the left and the right of the tank. This represents the front and the back of the tank. All right, this length is S, so there will be S times the width is also S plus 2 times the width is labeled as S, times h plus 2 times the length, which is s times h. All right, so if I simplify this, s times s will be s squared plus 2sh plus another 2sh. Well, if I combine like terms, 2sh plus another 2sh will be 4sh. So the surface area for this rectangular tank will be s squared plus 4sh. Okay, so that's our formula for the surface area of that tank. Okay, now we're also given something else in that problem, the volume of that rectangular tank. There's another formula that we should be familiar with, the volume of a rectangular prism. And that's this. V is equal to length times the width times the height. Okay. So maybe I should write this down here. V is equal to length times the width times the height. That's the volume of a rectangular prism. You're given that the volume was 19,652 cubic feet. So that's what V is going to be equal to, 19,652. That's equal to the length. That's going to be the S in this case, times the width, which is also S, times the height. Well, S times S is S squared, so 19,652 will be equal to S squared times H. And in this case here, I'm going to write the surface area equation in terms of S. I mean, in terms of, in terms of S. That means I need to solve for H. So I'm going to divide both sides by S squared. That would mean H is equal to 19,652 over S squared. Okay. And our area is this formula right here, S squared plus 4SH. So this H will be substituted with 19,652 over S squared. That means I have A is equal to S squared plus 4 times S times H, which is 19,652 over S squared. Now, one of the S's divides out. I'm left with the S in this denominator. So that means A is equal to S squared plus 4 times 19,652 will be 78,608 over S. So this represents the objective function. That would be your objective function. So in this problem here, the objective function there would be A is equal to S squared plus 78,608 divided by S. Okay. Now let's find the interval of interest of the objective function. Okay, so the interval, of course, lengths can't be negative. The lengths of sides can't be negative. And also, I'm going to get a 0 in the denominator. So the interval here would be from 0 to infinity. All right. So now we can find the dimensions of the tank that has the minimum surface area. Minimum surface area. All right, so I'm going to use this, and I'm going to write this as A of X is equal to, now A of S, since it's in terms of X, of S. So A of S is equal to S squared plus 78,608. I'm losing it here. 78,608. And I'm going to pull that S out of that denominator and write that as S to the -1. And then take the derivative of that. All right, so A prime of S would be this. The derivative of S squared would be 2S plus, well, actually it's going to be minus when I pull the -1 down. It will be a minus sign. 78,608 times S to the -2. Because the S has to be to the 1 less power when you take the derivative using the power rule. All right. I'll rewrite this as A prime of S is equal to 2S minus 78,608 over S squared. And then set this A prime of S to be equal to 0. That would mean 2S minus 78,608 over S squared is equal to 0. And then what I'm going to do is multiply both sides by the S squared to get rid of that S squared out of that denominator. As long as S is not equal to 0, I can do that. So S squared times 2S will be 2S cubed minus 78,608. S squared times that S squared in the denominator, that divides out, that's equal to 0. So to solve for S, I'll move the 78,608 to the other side. It'd be 2S cubed is equal to 78,608. Divide both sides by 2. S cubed would be 39,304. And to get S, I need to take the cube root of 39,304. In fact, I'll just cube both sides just to show you that I get how to get an S by itself. So that means S is equal to, and here I'm going to use my calculator to come up with the cube root of this. So in this case here, for the cube root, I'll press the math key and then select number 4 for the cube root. Then type in 39,304 and hit enter. This gives me a nice round, even number of 34. So the length of that side is 34. So if I want to answer the question, the tank with the minimum surface area has a height of, well, I'll come back to that, and it's square base with a side length of 34 feet. Because that S represents the side length of that rectangular tank. So it's this side right here and this side, since they're both equal, a square, it has a square base. So this is what, 34 feet, to be specific. Now to find the height, that was, and if I go back to this, 19,652 over S squared. So if I substitute that S with 34, and I have to square that. So it'll be 19,652 52 divided by 34, and we square it, we'll get 17. And this is going to be 17 feet. So going back to this right here, the tank with the minimum surface area has a height of 17 feet and a square base with a side length of 34 feet. Okay, so that's how we answer this example here. All right, and finally, the final example in this video is this. A rectangular flower garden with an area of 170 square meters is surrounded by a grass border 1 meter wide and on two sides, and a 2 meter wide on the other two sides, as shown in this figure. So now, what are the dimensions of the garden to minimize the combined area of the garden and the borders? Okay, now we're told to let H be the vertical height of the garden and let A be the total area of the garden and borders. Write the objective function. Okay, let's look at what we have here. We're dealing with a rectangle here. So in this example here, the area has to be length times the width. All right, and this is going to represent the area of the garden plus the grass that surrounds it. That area formula represents the area of the garden and the grass that surround it. Now let's look at this one right here, the flower garden. All right, that too is just going to be the area equals to the length times the width. This is the area of just the garden itself. And we are told that the rectangular flower garden has an area of 170 square meters. So here we're going to substitute the A in this formula with 170. That's equal to, and we're letting H be the vertical height. So that's H. And I'm going to let this be the width. That's W. So it's actually going to be W times H. Now let's find the length and the width of the flower garden plus the grass that surrounds it. Now we're told, let's look at this dimension right here going across. We got 2 meters going this way, and also, if you look at it, 2 meters going this way. So if I add the W plus 2, I'm going to end up with W plus 4. So all of this length going across is W plus 4. Now let's find this, the length of this side right here, which is a height. Okay, 1 meter here, that means from here to here, that's also 1 meter. And if this is the height going in this direction, 1 plus 1 plus the height, which is H, that's going to be H plus 2. So that means that the area of the garden and the grass that surrounds it would be this length times this width, or height. So it'd be W plus 4 times H plus 2. So let me fill this in. A is equal to W plus 4 times H plus 2. All right. Now, I want this formula in terms of H. So that means I need to solve this equation for W. So to get W by itself here for the 170 equals to W times H, we're going to divide both sides by H. So that means W is equal to 170 over H. And now let's substitute the W with 170 over H over here. So this will be A is equal to, W is going to be 170 over H plus 4 times H plus 2. And of course, we'll have to apply the FOR method here. So if I do 170 over H times H over 1, your H's will divide out. You'll be left with 170. And then the outer would be 170 over H times 2 over 1. Or 2 times 170 will be 340. Over H times 1, which will be H. The inside will be 4 times H, which will be 4H. Plus 4 times 2. That's going to be 8. All right. Now, if I combine like terms, 170 plus 8 is 178. So I have 178 plus 340 over H plus 4H. So this right here is your objective equation for this situation. That's your objective equation. So if we were to answer this, we'll just fill in 170 plus 340 over H. That's your objective equation. And then they ask for the interval of interest of the objective function. Well, our lengths cannot be negative. And if you look at this, I would get a 0 in the denominator here. So the interval will have to be in interval notation, everything positive, from 0 to infinity. And not including 0, by the way. So now we can find the dimensions of the garden to minimize the combined area of the garden and its borders. All right, so let me write this as A of H equaling to, and in this case here, 170 plus, and I'm going to pull the H out of the denominator, make that H to the negative 1 plus 4H. Now let's take its derivative. So A prime of H, the derivative of a constant is 0, so the derivative of 170 is 0. Bring this negative 1 in front of 340, it will be negative 340. Copy over the H to the 1 less power, so it'll be negative 340H to the negative 2, plus the derivative of 4H will be 4. And I'll write that using positive exponents. That'll be negative 340 divided by H squared plus 4. Now I want A prime of H to be equal to 0. So here A prime of H will be negative 340 over H squared plus 4 equal to 0. Now I'm going to multiply both sides by H squared. Since it's in the denominator. balance this off, and then this will be multiplied by h squared. So now, negative 340 over h squared times h squared, the h squares are gone. You're left with 340 plus 4 times h squared would be 4h squared equal to 0. And then we solve this equation for h. So add 340 to both sides. You'll get 4h squared is equal to 340. Then divide both sides by 4, you'll get h squared is equal to 85. And I'm not going to worry about the plus or minus here because we know lengths can't be negative. So I'll just take the positive square root on both sides. So here h will be equal to the square root of 85. And that is your local minimum. Since we're minimizing the combined area of the garden and the borders. Now let's find out what the width is. Going back to one of our secondary equations here, that width was 170 over h. So let's use that to find out what that width is going to be. So this is 170 over the square root of 85, which is what h is. Now we can't have a radical in the denominator, so we need to multiply the numerator and the denominator by the square root of 85. So this is 170 over 170 times the square root of 85 over the square root of 85 times itself is 85. Then if I divide 85 into 170, that's going to go 2 times. So that means the width would be 2 times the square root of 85. And by the way, this is in meters, by the way. So I need to mention what those units are. All right, so to go back to this example here, that interval of interest was 0 to infinity. We've got to fill that in. The vertical height of the garden that will minimize the total area, we found that out to be, in this case, the square root of 85. And that's in meters. And the horizontal width of the garden that will minimize the total area will be 2 times the square root of 85 meters. Okay. Now here they give you the units, but keep in mind, if you were taking a test, you will have to mention those dimensions, whether you have meters or feet or inches or whatever, you have to specify those units as you give your final answer. Okay. Now I know that these problems, that these examples I've done were a bit time consuming, but if you do a little bit of practice on this, you should be okay with these problems. And in the homework, there are problems that are similar to the ones that I've done in these examples. Okay, so that does conclude this video on section 4.5, dealing with optimization problems. Feel free to contact me or reach out to me if you have any questions about any of the examples that were presented in this video, or if you have questions about the homework that's in my math lab.